I only know it from my discussion with him, right, which was a few months back. So
Sir.
he did tell me that that they have developed this ontology related to code, like the code structure,
Yeah,
software code
yeah.
structure, right? So but yeah, beyond that, I don't have any idea on how they are using it.
No, no, not specifically that one. Okay, so yes, you are okay. So enlight or your idea about okay such kind of tasks. So if you
Actually,
wanted to pick up that task,
actually, Raghav, what he wants to say is the application of ontologies anywhere means, for example, Fani Kumar yesterday discussed about materials domain.
Right,
Dr. Srinivasa talked about program analysis. He has
nice.
utilized ontologies. So,
right.
what else? Just a minute on X, Y, and Z where the ontologies can be used.
Oh, okay. So wherever you need, so whenever you're doing some task, right, all this knowledge would be inside the head of these domain experts. So for example, you're building an application related to, I don't know, some healthcare. Right? So either you have to talk with the doctor, or if you already know the domain, you can, it will be in your head and you will be implementing it based on whatever you already know, right? So the advantage of these ontologies is now you take this knowledge out, like you can put it out, so that it's shareable by different applications. So let's say there's someone else like me who is building again a healthcare application related to the same domain. I don't know, cancer or whatever. Right? You built one app and I built a different app. So I can reuse whatever uh, the domain that, sorry, the knowledge that you put out. So that's it. So in that sense, you can use it for multiple different domains. Obviously, healthcare is a very popular biomedical field, and healthcare, that's a very popular area for ontologies. But this is new, whatever Professor Srinivas Kumar has described, right? So I didn't come across these ontologies in that particular space. But there are a lot of other domains, like geoscience is very popular. Then you have oil and gas, and aviation. So all these, so there are different fields, and ontologies are pretty popularly used in all these different domains.
so in your experience, okay, so what sort of ontologies you developed or okay, so you use it for which applications kind of in real? Have
So
you?
so right now, so I'm working with a healthcare startup, and they are working in this neonatal space. So similar
Neonatal.
to ICUs, right? So we have intensive care units for the
Yeah.
adults. So there are intensive care units for neonates as well. So neonates are babies who are born before their term, right? So generally 40 weeks is
Yeah.
considered to be the right time. So or
Yeah.
around 40 weeks.
8 months or
But if they
9 months.
are born before that, let's say before 34 weeks, for example,
Yes, sir.
they are called as preterms, and they are the neonates. So if they are born even earlier, let's say in 23 weeks or let's say 28 weeks, not all their organs are well developed, right? So they need to be, uh, so special care needs to be taken for them. So they are put in these NICUs, neonatal
Yes.
ICUs.
Yes, sir.
So I'm working with that startup, and then we are building some ontologies related to the medications that they need to take, and then the nutrition that they need to take, and so on. Again, so this again comes under the healthcare domain. Right? So
Yes, sir. Specifically
yeah, so that's
related to
what.
that neonatal one.
Yeah,
Okay, okay.
neonates.
Excuse me, Dr. Raghava. This is Sanju.
Yes. Yeah. Hi,
Uh,
Sun.
Hi. Actually, I have a question about the vocabularies. Like yesterday, Dr. Asha has explained about the control vocabularies. But if you have, I want to know like agrovoc and bio-ontologies, there are a lot of vocabularies. But if you, I want to know if you have a bunch of ontologies, then how can you create a control vocabulary for your own domain, particular domain? Like you are talking about the healthcare domains. Then if I have different 10, 20 ontologies related with the healthcare, so I want to include all of them in a control vocabulary. It should be my own vocabulary. I want to present it. So could you give me some idea about this?
So is it about utilizing the existing vocabularies in your ontology, reusing
Sorry?
it? Is it?
Sorry, yeah, I can use, or I can have my own. It depends. Like I have 4 or 5 ontologies, and I want to
Okay.
present it as a vocabulary. Like vocabulary is a collection of, as I know, I'm not sure, but as vocabularies is a collection of ontologies. Like AgroBook and BioPortal have a lot of ontologies there.
Oh,
So
so repository. Yeah, yeah.
yeah,
So
repository.
okay.
Yeah,
So you want to build a repository of these ontologies, is it?
yeah.
Okay. So yeah, that can be done, but my suggestion would be to submit to one of these popular repositories, like the ones that you said, right? If it's possible, because they are already indexed and people are aware of it. And if they search, or you can post it on your website also. But yeah,
Uh,
but the advantage, I don't know. So if you have a good search interface on top of it, then it becomes easier for and people to search and get it, right? Like let's say there's a popular one called LOV, linked open
Yeah,
vocabularies,
yeah. They have different domain ontologies. Though, so
right? So
how can
it's
I
easy
put?
to search and get it, huh?
Okay, all right.
So if
Thank you
possible,
for
try
this.
to submit there. I think LOV, because then, like I said, it's already
Like,
popular, and then people can, if they search, they
yeah,
can find your ontology and
yeah.
they can reuse it also.
Even we can store the ontology at BioPortal. We can store on other other AgroVoc and some other repository. We can store there my own, but they are not my own vocabulary. They are others' vocabularies. They are others' repositories. So it was. I'm trying to find it, but I didn't get, not yet. Thank you.
Okay, if you're,
Yeah.
so if it's one of the popular repositories like the ones that you said, then it's easy to find. So that's the advantage, right? So you can easily find those ontologies in those repositories. But if we try to build our own, like it's like reinventing the wheel. So better to make use of the existing ones.
Okay. All right.
Uh,
Thank you.
Thank you, Raghava. I
Definitely.
think now we can start the session, and Dr. Fani has already joined us. And I do not remember how many times he named you in his talk yesterday. He was
Oh,
recalling you, he was remembering you much. So all of us are waiting to listen to you.
oh, thank you. So there's too much expectation. Oh, okay. Just to answer, so I'll add one more point to Sanju's question, right? So these are a
Yeah.
plug for our own work. So there's so so one of my students, he developed this plugin. So Protege, by now all of you know about Protege, right? So it's a ontology editor. So there's a plugin that can help these ontology developers. So while you are developing your ontology on the using Protege, it can suggest other classes and properties that you can reuse. So it will look up these repositories, and it has already indexed these repositories locally, and then it will suggest these classes, properties, axioms. Um, so we didn't cover design patterns, ontology design patterns, but it can also suggest ontology design patterns. So the idea is that it will make the ontology development process a little smoother, especially for people without much experience. Right? Because one of the good practices is to reuse as much as possible existing ontologies or vocabularies, or at least terms in these ontologies. Okay, so with that, so the name of this tool is Ontos here. I can put it in the chat. Uh, yeah, I can. So it's a plugin, and you can download it and then use it along with Protege. Okay, so with that, I can get started with my talk.
Please. Yes, please go ahead.
Okay, so we'll be talking about. So I think by now you are all familiar with what are knowledge graphs, right? So I'll be talking about the querying aspect. So how do we query these knowledge graphs using a query language called SPARQL? Um, so it's okay. So there are so the most recent version of SPARQL is called SPARQL 1.1, and it has made a lot more additions compared to the previous version, which was 1.0. And so earlier, SPARQL used to stand for a recursive acronym, but I think people have now moved on and they dropped it. So now it's just it stands by itself, right? There's no it's not a short form. It's a language, SPARQL, and it incorporates two sets of things. One is the query language itself, and the other one is the protocol. So, okay, I'll discuss these different aspects of SPARQL briefly, but we'll be focusing on the query language part, which, okay, I'll talk about it later, but there are other aspects also, like what should be the result format. So there are a couple of formats that it supports, like XML, JSON, CSV is the comma separated values, TSV is the tab separated values. So what should be the format of the query result? So this aspect talks about the result format, right? And then there is one more part of SPARQL which talks about federated query. So I'll also briefly discuss about what is an endpoint, but you can think of it as a REST service, right? So let's say you have I don't know if are you all okay with using this term REST service, or should I? So it's like a web service, for example. So let's say you have you are hosting a web page and you are opening a port, right? A specific port, let's say 8080 or whatever, 8081, and now people outside of any client can now hit on this port, and then it can request for information. So that information can be a web page, or it can be a specific query. So it can ask for say list of documents that can satisfy particular criteria. So all these different types of queries can be put to that particular server, and it can receive all these queries through this particular port which is open for public, right? And it can process the query and give back the results, right? So the results can be HTML documents, or it can be say XML files or whatever. So that is what is generally called a service or a web service. So federated, so similar to that, there are also SPARQL service, which we call it as endpoint, right? So if you again, so that particular port and URL is exposed to the public, and you can send in your queries to that particular port on the which is processed by the server, right? So it can take in these queries which are sent over the web, and it is processed on the server by the server, and it will give back the results. So that is what is called an endpoint. So now federated querying is about sending these queries to multiple different SPARQL endpoints, right? So let's say you have you would like to query multiple different databases or RDF graphs, for example, and they are sitting in different locations, but you want to have a integrated query over all these let's say 3 different RDF graphs. So now the SPARQL engine can take in this query. It can split that into different pieces, the small pieces, and each piece goes to the individual server that can answer this query, and then it has to put back the results and send it back. So that is federated query, right? And we won't be talking about it here, but so if you are interested, you can go over all these different aspects, right? So the other one which is pretty recently introduced in SPARQL 1.1 is the entailment regimes. So this talks about the inferences. So for example, so we briefly talked about these inferences in my session on the very first day, right? So let's say you have again, I'll give the same example. So you have 2 facts: all birds fly and pigeon is a bird. So based on these 2 facts, if you are asked a question, can pigeon fly? You would need to do some inference, right? Because I didn't exactly give out the fact that pigeon can fly. So you need to make some inference and then answer this query. So if you can, so if you ask a question through SPARQL, and if it's needs some inferencing, then the SPARQL engine, underlying SPARQL engine, can do that and then give back the results. So it can only do that if these entailment regimes are supported, right? So this is a new edition, and any SPARQL engine that supports SPARQL 1.1 should be able to do these entailments. So entailments is a synonym for inference. Right? Both are similar. So that's about entailment regimes. And the other aspect is the update. So earlier, so until SPARQL 1.0, SPARQL used to be a read-only kind of query language, right? You can, you have a graph, so it will treat it, there is no way to modify that graph. So if you are, if you take the analogy of SQL, right? SQL, sorry, it is the query language for relational database. You can update the tables, you can drop the tables, and so on, right? But until SPARQL 1.0, you couldn't do all these things. You can only retrieve the data from the RDF graphs, but you cannot change it. But that has been changed since SPARQL 1.1. You can now update the existing graphs as well. Right? So that's about SPARQL 1.1 update language. So most likely we will not have time to go over this as well. Okay, so there are a bunch of other aspects of SPARQL 1.1, but I think I'll just skip, right? So and get started with the actual querying language. Right? Okay. So to start off with, it is very similar to SQL or SQL. So whenever you see all these different features or constructs that I'm introducing throughout this session, right, you can easily relate that to SQL. So if you know SQL, and it will be a very easy transition to start using SPARQL, right? And I think that was one of the design choices as well. If it's similar to, say, popular existing language, then it's easy to pick up and start using it, right? So so that was the motivation behind it. So okay, the one of the primary purpose of SPARQL is to query the RDF graph. And as you all know by now, that RDF is a directed label graph. So from that point of view, SPARQL is a graph pattern language. Right? So you can specify a few patterns. So when I say pattern, you can think of regular expressions. Right? So in regular expression, you can put out a pattern, and that pattern should match any given sentence. Or so, for example, you can write a pattern to match the phone number. So that means it should have exactly 10 digits. Sorry, it should have exactly 10 slots, for example, and each slot should be a digit. So there should not be any alphabets and so on. Right? So if you have a pattern, you can match this pattern to, let's say, a file containing, say, text and numbers. So now you can filter out. Right? So it's similar to that. So SPARQL is a pattern language, but it's applied on graphs. And then whatever part of the graph that matches this pattern is retrieved and given back as the result. So at the high level, that's how it works. And like I said earlier, it's similar to SQL. So in that sense, it also supports aggregation, subqueries, negation, filters, and so on. Okay. So there are a few important terms which I'll introduce. The first one is this binding. Right? So as part of this pattern that you specify in the query language, you will be using some variables like X, Y, and Z, for example. Whenever the pattern is matched with some part of the graph, let's say a subgraph, we call that as a binding. So each variable is now bound to something in the graph. So that could be a constant like Alice, for example, or a URI or a IRI, for example. So this is the IRI here. So it can refer to anything, right? So X can be subject, predicate, and object. It doesn't matter. But it's a binding that happens whenever the pattern is matched with subgraph. So you represent this as a pair, binding as a pair. So you have the variable and then the RDF term. So RDF term can be either, like I said earlier, it's an IRI or a literal or blank node. So we haven't discussed what a blank node is, but I think it's not required for at least for this session. But if you are interested, please do check what blank nodes are. So the other important term here is what are called as basic graph patterns or BGPs. So basic graph pattern is nothing but a triple. So you have your subject, predicate, and object, except that any one of these terms in the triple, either subject or predicate or object, can be a variable. Right. So you can either bind them beforehand. So you can say that give me all the faculty members of IIIT Delhi. So in that sense, you are so if you take one example, which is Raghava works at IIIT Delhi. So now you are looking for all the members who work at IIIT, right? So in this case, work set is fixed. So the predicate is fixed, the object is fixed, which is IIIT Delhi. So the only variable here is the subject, right? So that's one example of a triple pattern. So it's similar to a triple, except that any of these terms can be a variable, right? So I'll start with the different features of SPARQL, starting with the most basic one, which is the select clause. And like I said, this is very similar to SQL, right? So it's used for projection, meaning, so let's say you have these patterns, different patterns that you put out, but among them you are interested in only a few of these specific variables, right? Like for example, you are looking for all the courses taught by Raghava at IIIT. So there can be multiple variables involved here, but you are only interested in the course name and the course ID, right? So that forms the projection here. So you select only those variables that are of interest to you. So that can be possible through the select clause. So let me go over an example, right? So let's say this is the triple that we have. You have book 1, and the title of the book is SPARQL tutorial. So in this case, this is a literal or a constant. So the object is a constant. You have the subject and predicate, which are IRIs. Right? So now we can write a query something like so. We are interested in retrieving the title, and we are also specifying which book's title we are interested in. So that's book 1, and the predicate here is title. The variable is, since we don't know what the exact name is, we are replacing it with a variable. So the variable always starts with a question mark. Right? And each BGP, which is the basic graph pattern, should end with a dot, except the last one. So since there is only one, you could have skipped the dot, but it's anyway a good practice to always end each BGP with a dot. Right? So what do you think should be the result of this query? So one of you can unmute and let me know the answer.
SPARQL tutorial, sir.
Right. So yeah, that's it. So we are interested in this particular variable, and this is the binding, right? So this is the binding for that variable. So a literal has been bound to this particular variable, and so this is the, as you would have guessed, this is the result of the query. So let's go to a slightly more complex example where we have multiple different tuples. So this is one of the serialization formats for RDF, which may not have been discussed in this particular TP, right? So there are different ways to write these graphs. So serialization would mean to different mechanisms to store this graph, right? Eventually, you would have to write this graph to a file and then store it on some physical space, isn't it? So there are multiple different ways or formats to write this graph to a file. And the example that I have shown here, that is one of the formats, right, which is called as N-triples, NT for short. So you can ignore the prefix for now, but and then just look at these triples, right? So you have one triple which says that the name of this particular resource is Johnny Lee Outlaw, and then you are also describing the mailbox. So there are two aspects that we are describing here. One is the name of that person and the mailbox of that person, right? So that's the data that we have. And now let's write a few queries. So we are interested in retrieving the name and the mailbox. of all the people, right? So here we have a join. Okay, so this is the first BGP that I highlighted here, and then you have your second BGP. So in the first BGP, we are requesting for the name, and in the second BGP, we are requesting for the mailbox. But there is a join here because we are using the same subject, right? In both the cases, the subject is the same. So it's the same resource. For the same resource, we are requesting the name as well as the mailbox. So whoever is X, that X should have a name, and that name is a variable. And for the same X, we are requesting for the mailbox, and we don't care what that mailbox is. So we left it as a variable, right? And in the projection, we are interested only in the name and the mailbox, so, and not X, right? So we skipped X, and then we are saying that we are interested only in the name and the mailbox. So that's why we use only these two variables. So in this case, what do you think would be the answer? The query result. So you would obviously have two columns, name and mbox. So now what should be the, you can tell me the number of rows and then the content of each row.
The two names are Johnny Lee and Outlaw and Peter Good Guy. Names are there. And the mbox JLO example.com and Peter example.com.org.
Okay. So why do you think Carol doesn't show up?
Not sure, sir.
Okay, so the answer is correct. But so it's important to know why Carol doesn't show up, right? Because so for the same person, you are requesting the name and the mailbox. So both are required, right? Both are these. There are two conditions that you specified.
Yes, sir. For Carol, there is no name.
Yes, so both these conditions should be met. So
Yes.
in this case, you have Johnny Lee, and Johnny Lee has a mailbox, so that condition is met. You have Peter and the Peter's mailbox, so the condition is met. But in the case of Carol, you only have the mailbox and not the name.
No.
Right, so in that case, both the conditions are not met, so the join in that sense is not successful. Right? So that's why you only get these two rows as the output. So later on, we'll see other mechanisms where you can say one of the conditions is, one or more of the conditions is optional. Okay, one more example. So in this case, we are talking about two books. So both the books have title, price, and a discount. Right? The name of the first book is SPARQL tutorial, and the name of the second book is the Semantica. So this is the data that you have, and now you want to retrieve the title as well as the discount. So after discount, what should be the price? Right. So the discounted price basically. So you want the title and the discounted price. So similar to SQL, so you can also do this in SQL. You can write these expressions as part of the select clause and then give a name to that expression. So you have done some math here, which is an expression, and now using this as, which is a keyword, you are giving a name to this particular expression, which is price in this case. Okay. So you can do that in SPARQL as well, similar to how you do in SQL. Right? So now the rest of the query follows. So there are three BGPs here again, and there is a join on the subject. Right? For the same X, you are requesting for the price, title, and discount, and you are simply calculating the discount, the total price after the discount. So this is pretty straightforward. So you get your title and then the price after discount. So any questions so far? Okay, so yeah, let me move on. So at a high level, there are 3 or 4 features or constructs that are part of the SPARQL query language, right? So one is select, the other one is construct, which we will see now, and the third one is ask. So using ask, you can only get these Boolean results, right? So you can, so it is very similar to your exist clause in SQL. So you can check whether some subgraph is part of the graph, and it will return true or false. So that is the purpose of ask. And then the fourth one is called describe. So one of the disadvantages with interacting with graphs that are already out there in the web is that you don't know the structure, right? You don't, for example, I created an RDF graph and I posted it on my website. So it's very hard for you to know what the structure is if there is no good documentation, right? So that's why the documentation is very important, right? So in your documentation, you should describe what are the major concepts and how is the graph related and so on. So it's also good if you put out the ontology for that graph. But let's say if you don't have any of these and you want to understand the structure of the graph, so then you can use this describe feature of SPARQL. So you can say describe the any particular concept X, and you can name the concept. So say describe Raghava, for example. So there's a graph on IIT Delhi's faculty, and you can say describe Raghava. So it will give out all the edges and then the other neighboring nodes that are connected to Raghava. So then you can try to understand the structure better, and then you can start querying that graph. So that's about describe. Right. So at the high level, you have these four major features of SPARQL. So all the queries that we discuss fall into one of these four categories. So it's either a select clause, part of select clause, or construct, or ask, or the last one is describe. So we have seen select. So now let's briefly look at what a construct is. So in your using your select, you can retrieve the answers. Right? So you can have these bindings, but they are not in the form of RDF graph. But let's say if you want your answer back in the form of RDF graph, you can use this construct feature. So the advantage with that is you can have a select on top of a construct. So you can do some construction of the graph using the existing graph, and then you can have select on top of it, right? So the other advantage is, as we'll see in the examples, we can also change. Okay, I shouldn't say change, because it's not changing the existing graph. So you can make some changes to the graph and then put it out as a new graph. Okay, so I'll explain this aspect with an example. So let's say you have these triples. So there are two people, A and B. A's name is Alice and A's employee ID is 1, 2, 3, 4, 5. And you have your B's name, which is Bob, and B's employee ID. Right? So now you want to retrieve this as a graph so that you can query on top of this new graph. Right? So using construct, you can build this graph. So it's a simple graph which has say one subject and one object and a predicate, right? So whichever triple satisfy this pattern, it will be retrieved. So here you are looking for all such X which have a relation called fourth name, and it could be any name. So in this case, you will be getting two triples as output, right? So just for this particular line. So you will have a employee name Alice. Oh, sorry, okay, I'm going it in the. So I explained it in the other way, in the reverse direction. So first is the where clause will get satisfied, and then you do the construction. So you need to just reverse whatever I said. Right? Sorry about that. So first look at this X, all such X which have an employee name of any name. So you will get these two as the output, right? First is you get A employee name Alice, and the second output would be B employee name Bob. Right? So that's the output of this particular where clause. So now using this output, you want to construct a graph. So that construction happens using this particular pattern. Right? So what we are trying to do is we are simply trying to create one more graph that has a different predicate name, right? Different predicate. So earlier the relation name was employee name. You simply want to say reuse the FOF vocabulary. FOF stands for friend of a friend. It's a popular vocabulary that can be used to describe any person. So things like the name of a person, address of a person, the mailbox of a person. So if you are trying to model any of these, it's good to reuse the FOF vocabulary. Right? So yeah, so the idea is to create a new graph, so it doesn't make changes to the existing graph. Right? That's part of the update language of SPARQL. So we are only constructing a new graph where the relation name is FOF name. Right? So now on top of this, you can again build a select clause. So there can be a select here where the inner query would be a construct, but and maybe we'll look at it later. So did you understand this construct or how it can be used? So now the output of this construct is an RDF graph. Any questions on this one before I move on?
Excuse
There's
me,
one
sir.
more example, but yeah.
Excuse me, sir.
Yes.
Sir, the graph constructed by construct, is it temporary or it will be stored where the original
Right.
graph?
Yeah. Okay. Yeah, that's a good question. Yeah, it is temporary. So if you have a select on top of it, then you can further query it. But yeah, if you don't store it anywhere, then this is gone, right? So when after you are done executing this query, you no longer have this graph.
Okay, sir. Thank you. So it is similar to view in SQL maybe?
Right. Yeah. So in view, at least the name is available. Yeah? You can give
Yes.
the name to the view and it's there, but the results are computed at runtime, right? But in this
Yes,
case,
sir.
it's you can't
Okay.
even name it. It's an anonymous RDF graph that exists only until the end of this query,
Okay, sir. Thank
unless
you so
you
much.
save it explicitly. Okay. So this is the result of the construct query, right? So now you have a graph, although it's a disjointed graph. Right? You have two triples which are not connected to each other, but it's a graph. So you have a graph, and you wanted to change the relation name, and that has happened here. So okay, let's look at one more example where we have a slightly more complex example, I guess. Okay, so you have one person here, and that person's name is Alice, and you have the mailbox of Alice. Right, so you can ignore the prefix part and just look at the rest of the query. Right? So you have your where clause where you are retrieving all the triples that have a relation called FOF name. So in this case, it's only just one triple, right? You have a FOF name Alice, so that gets retrieved.
Hello, sir.
Yes.
Sir, as you said, it is a temporary graph after extraction.
Right.
Is there any mechanism to store is there any concept to store that temporary for future
Yes.
reference?
Yes. So we'll not be looking at those aspects. So there is something called load. So that's a feature of SPARQL, LOAD. So using that you can load this graph into a particular again SPARQL endpoint. So there are SPARQL engines or triple store. So the general term that is used is the triple store. Just like your relational database, if you store these triples, it's called a triple store. Or a general term is the graph database. Right? Eventually it's a graph database. Right? So and these graph databases, they can have this service or the endpoint, SPARQL endpoint. So you can specify that this graph should be loaded into that particular endpoint.
Okay, sir.
So using load, you can do that.
Okay, sir. Thank you, sir.
Okay, so here you want to again do some changes to the graph by constructing a new graph. So in the new graph, the subject is Alice. So you are explicitly specifying the subject. And again, you are trying to reuse a existing vocabulary, which is vcard in this case. Right, so it's a virtual card. So similar to your contact card, which is physically printed and given. This is a virtual card, right? And your FN is the first name. So you want to construct this graph where the relations comes from the vcard vocabulary, and you are making use of the first name relation from that vocabulary. And the name, whatever name comes here, would be bound to this particular name. So the output of this construct query would be a graph that has only one triple, right? So Alice, first name Alice. So that's about construct clause. So next we'll be looking at filter. So there are two parts to the session. In the first part, I'll be going over these different SPARQL features, and in the second part, we'll be looking at some specific queries and the output that they give. Right. So I'll run them over these SPARQL endpoints, and then you can see the results, and we can discuss the query also. So I'll talk about these different features for, I don't know, 10, 15 more minutes, and then we can look at some of these queries, right? Okay. So next clause is the filter clause, and again, this is pretty similar to your SQL, right? So you can filter out a few terms. So you need to give an expression as input to the filter clause, and this expression can result in either true, false, or error, and solutions that result in either false or error, they are eliminated. So only the ones that are true would be taken for further processing. Right. So let me give an example. So you have two books here, and we have seen this data earlier, right? So you have two books. There's a title and price associated with each book. And now let's say you have a query. So you are interested in the title of all the books that satisfy this criteria. So the pattern that you are interested in is retrieving all the titles. So irrespective of whatever title it is, you want all the titles, right? But in the filter clause, you are putting in a regular expression. You are now saying that I'm only interested in those titles that start with this particular set of characters, which is SPARQL, right? So the caret symbol indicates that the title should start with this particular set of characters. So rest of the title can be anything else, right? You don't care. So you're only looking for those titles that have the starting word as SPARQL. So in this case, the semantic web title gets filtered out, and you have only one result, which is SPARQL tutorial. Right? Is that clear? Okay. So let me move on to another example, right? So it's the same data again, but in this case, you change the regular expression, and now you are interested in all those titles that have the term or that have the characters WEB in them, web in them. Right? And I indicates that you can ignore the case. So either it can be capital case or small letters, it doesn't matter, and any of one of these characters can be in small or capital. Right? For example, in this case, W is capital, but you can ignore the case and then do the comparison. So that's what you are specifying here, right? So you can do that, and then so there's only one title that matches this regular expression. The other title gets filtered out, so you get only one as the result, the semantic web, right? So that's about the filter clause. Any questions so far? Or should I move on? Okay, so let's go to the next one, which is optional. So sometime back, I mentioned about these joins, right? Joins on the subject. So if you have two basic graph patterns, and if the subject for both the basic graph patterns is the same, then you are joining by subject. So here, the condition that you are specifying is both these criteria should match. So let's say you are looking for people who definitely have a name and a mailbox associated with them. But let's say in some cases, there is a name but no mailbox. But even in those cases, if you want to retrieve those kinds of triples as well, you can use this optional clause. And as the name says, okay, I'll show with an example. So let's say you have these triples. So it's talking about two people, Alice, and Alice has the type information associated with it, the mailbox and the name. And then you have your B, which is Bob, right? So notice that Bob does not have any mailbox. Right? It's only the type and name information associated with Bob, right? So let's say you have a query now. So you are interested in retrieving all the names along with their mailboxes. So if you don't have this optional here, right, it's a join on, it's still a join, but it's a join on the subject. But both these criteria should be met. So you're interested in only those X that have both the name as well as the mailbox. But when you say it's one of them is optional, that means it is okay if some triple has or some person has just the name but not the mailbox, right? So and this is what you get. So in this case, Alice had 2 mailboxes, so that's why it got repeated twice. And Bob, in Bob's case, there was no mailbox, but you said it's an optional anyway, right? So that's why the mailbox part for Bob is empty. And is this clear? So let's go to a slightly more complex example. So you again have book 1 and book 2. They have, okay, we already looked at it, right? So there are 2 titles and there's a price associated with both the books. And now you're interested in getting the list of all the titles along with their price. But there is a clause associated with it, right? So you are also filtering those books that, so you're only interested in books that are under 30. So whatever is the unit. So here we don't specify the unit, so it can be say rupees or dollars, or whatever, euros or whatever. So you are only interested in those books that cost less than 30. But since you are keeping it as part of the optional, that means you are also okay to take a look at all the titles, but you are more interested in books that cost less than 30. Right? That's what this query means. So you have the join on the subject. For the same subject, you are interested in the title and the price, and the price should be less than 30. So you have, in this case, you have only one book that satisfies this criteria, but since the price was optional, it also ended up retrieving the other book, right, which is SPARQL tutorial. So is this clear? Okay, we have slightly more different. So it is different and sort of slightly more complex, right? So you have your 2 people here, Alice and homepage associated Alice, but for the second person, you have the name and the mailbox. In the case of the first person, the mailbox is missing, and in the case of the second person, the homepage is missing, right? So in this case, now you are interested in the name, mailbox, and homepage, but you are saying that only the name is optional. Sorry, the name is compulsory, but the other 2 criteria is optional. So this person may or may not have a mailbox, and they may or may not have a homepage. So you are okay to sort of skip this, right, if it's not there, and you end up with these kind of answer. Because in the case of Alice, she does not have a mailbox, but she has a homepage. But in the case of Bob, he does have a mailbox, but he does not have a homepage. Right? Is that clear? So I'll go over a few of these aggregates, and then I'll skip to property paths, which I think is interesting, and because that is something that's not available in SQL. So all these things that you see here, most of them are available in SQL, and I think you would be most likely familiar with it, right? So because group by is available, count, sum, min, max, average, they're all available in SQL. So only these 2 features are new to SPARQL. Okay, so I'll give say 1 or 2 examples, and then we can maybe move on to property paths. Okay. So you have this data which talks about organizations and the books that are part of that. So you have authors who are part of organization, and there are books written by these authors. So in this case, you have author 1 and 2 who are part of organization 1, and author 1 has written 2 books, book 1 and book 2, and there's a price information associated with each of these books. Right? And you have one more organization with author 3 who is part of that organization, and author 3 has written it. Right? So that's the data that we have. And now we are interested in some aggregations. So one is the sum. So per organization, what is the, for each organization, what is the total price of all the books? Right, and you are also trying to impose some criteria on it. So the price should be at least greater than 10, or should be, sorry, it should be at least 10 or more. So okay, so these are the basic graph patterns. So you start with all the authors who are part of the organization, and the author should have written some book, and that book should have a price. So using this price, you are filtering, you are making the filter, and this is the having. Again, this is the same keyword that you use in SQL as well. And then you are computing the sum, and you are also giving a name to that particular sum of the price, right? So in the case of org2, the criteria is not met because org2 has one author, and this author has written only one book whose price is 7. So this criteria is not satisfied. So the only organization that satisfies this criteria is organization 1. Right? So that's how you have only one row in the result. Okay, so I'll skip this. So group concat. So as the name says, it's a concatenation, right? So you can concatenate all the, for example, all the names here. So I'll skip. Yeah, okay. So we anyway have property paths. So this is an interesting feature of SPARQL. Simply because, okay, one, it cuts down the amount of writing that we need to do in the query, and the secondly is something that's not available in SQL. Right? So let's take a look at this property path. So a path, so the path term comes from the graph, right? So a path could be any sequence of say edges, right, between a source node and a destination node. So that path can be of any length. So all the basic graph patterns that we have seen, the length of that path is 1. Right? So if I go back here, okay, maybe one more. So this is a basic graph pattern, right? So here the length of the path is 1 because path refers to this edge, and there is one edge that connects auth with auth, right? So this is a BGP of length 1, or a path property path of length 1. But if you have, but as you may guess, now you can concatenate more paths to the same BGP graph pattern, right? And you can shorten your SPARQL query by quite a bit. So let me just start with a few examples. So let's say you want to match one or both of these possibilities, just like an optional, for example. So you are interested in all the books that have title or label or both, right? But you are interested in all such labels of this book. So this pipe symbol indicates the or. So you are interested in title or label or both. So any book that has either or both of these should be part of the result, right? That's what this indicates. You can also have a sequence, which is the slash symbol, /. So what the way to read this is X knows someone. So that's an anonymous variable here. So assume that there is a variable, and that variable name is name. Right, so you are trying to concatenate two paths together or two BGPs together into one. I'll show you. Okay, there's an example here, and I think that could make it clear, right? So, so the question that the thing that is of interest to us is finding the names of people who are two 4 nodes links away. So that means if I know you, and you know, say X knows Y and Y knows Z, then I'm interested in X and Z because they are 2 links away. And let's say I want to say make a suggestion on say Facebook, for example. saying that okay, these are people who are 2 links away, then maybe there's a chance that X wants to become a friend of Z, right? So that's one application. So let's say to shorten that, you can write this property path. So X knows Y. So assume there's a Y here, implicit Y, and Y knows Z. And now you are interested in the name of Z, whatever be that name. Right? So there's a question mark here. So this is a query which can be written using property path. But if you write the same query normally, right, without property paths, it will become this bigger query. So where you have to write 4 BGPs. So you have your mbox, which is also here. Then you say X knows A1, A1 knows A2. So X and A2 are now 2 4 nodes links away. And you are interested in the name of this A2. So X and name show up in the select clause. So it becomes, as you can see, a lot more simpler if you use a property path. And this is a new feature in SPARQL 1.1, right? So these used to shorten the SPARQL queries. So is this, are there any questions here? Or is this clear? So I'll go over a few more examples, but yeah, you can stop me at any point of time. So second one is, okay, one more example. So this is something that you want to find. Someone Alice knows, okay, may well know Alice. So this is a sort of twisted example, right? So basically you want to try to filter out these duplicates. So if X knows Y and Y knows Z, which is the same as earlier, it can turn out that it's a, if you imagine it in the form of a graph, it can be a path that comes back to the source. So in that sense, the source and the destination are the same after 2 links. So let's say X knows Y and Y knows X. So there is a 2-way link. So they know each other already. Since they know each other already, there is no need to, for example, in the Facebook application that I said, there is no need to make any recommendation, right? Because both of them know each other. So you want to avoid those cases where X and Y know each other. So in that case, you can add a filter clause, right? So you are again going back to the same property path. So X knows Y, or let's say X knows Z and Z knows Y. But you want to avoid this case where X and Y are the same. So that's why you added this filter clause, so that X and Y are different, right? And now you are retrieving the name of Y, which is okay. Okay. So the other feature of property path is using these inverses. So you can also construct some short queries using these inverse property paths. So in inverse, you simply reverse it, right? So for example, you have your triple such as X mailbox is this Alice. But if you use the inverse, you have to first use this caret symbol. And then whenever this caret symbol is used, you simply internally, you can just swap this subject with object. So the second BGP is same as the first BGP, except that using this inverse property path, you swap the subject with object, right? So the way to read it is from, say, left to right. So you have X mailbox Alice. So let's see one example, and then maybe you can appreciate the utility of this inverse, right? So, okay, the example is find all the people who know someone. Who know someone X also knows, right? Let's say, so it's a sort of intersection, right? So I know someone called Y, and now I need to find all the people who also know Y. Right? Let's say I know Dr. Sarika, and now I need to find all the people who also know Dr. Sarika. Right? So that's what that's the aim of this query. Okay, so using this inverse property path, we can just write one line and we are done. Right? So I mean, you need to write the filter, but it's basically one line, right? So what this says is X knows says Z, and now Y. So whenever there is a caret, you read it from say right to left, right? So starting from the the opposite direction. So y also knows z. So x knows z, y knows z. So now I need all such y's who have a common z. Right. So, and the only criteria is x and y should not be the same. So if you write this in the form of a regular query, this is what it will be. So x knows a and y also knows a, and you are interested in all such y's. So again, going back to the Facebook friend recommendation, if two people know the same person, then there's a chance that x or x would like to be friends with y, right? So maybe you want to recommend such y's to x or x to y. Right? Is this clear so far? Okay, so let me introduce a few more features of property paths. Was there a question?
Not a question. I was just interrupting that. It is perfectly fine going on. So I think we can continue.
Okay. So now I just want to, okay, after, I don't know, a couple of slides, I'll switch over to some examples of using SPARQL.
Yeah, I know. Right.
Okay.
Please.
Okay. So let's say you want to add this. So okay, in regular expressions, you can do this, use this plus and star, right? So plus indicates one or more, star indicates 0 or more, right? So it has the same meaning here. So let's say you have a long path, property path, or say a long path in your RDF graph. So x knows y, y knows z, z knows say a, and so on. And you want to just write, you're interested in all such nodes relationships. Yeah, okay, sorry. So you're interested in all the people who know Alice, and they can be of any length, right? So say Alice knows Bob, so you show up. So Bob knows Alice, so that is one property path of length 1. And let's say Bob knows Mike. So indirectly, Alice also knows Mike, right? So you also want to retrieve Mike. And let's say Mike knows John. So there's an indirect link between Alice and John. So you also want to retrieve John. So to simplify that, you have this plus sign. Okay, so this is the query, right? So find the names of all the people that can be reached from Alice. So the length can be of any number. So it can be 1, 2, 3, 4, or 5. You don't care about that. If Alice knows them either directly or indirectly, then you are interested in all such names. So you can simplify all this just by using this plus operator, right? You simply say x knows, plus meaning 1 or more, and then you are interested in the name. So you can also mix and match these things. So you can say alternative. So ancestor, mother of or father of, one of these relations can hold, and there can be multiple one of them. So it can be one or more of these relations connecting ancestor to this particular me object, right? So all these are basically ancestors, right? So it is a family tree. So let's say you have X mother of Y and Y father of Z and Z mother of me. So you are interested in retrieving all such ancestors. So that's the query here. But you can simplify that into one line using these property paths. Did that? Are there any questions here, or is this clear? Okay, so let me move on. So you can also do some limited inferencing here using these queries. Sorry, using these property paths. So let's say you are interested to retrieve all the subclasses. Right? So X is of type, say Y, and now you are interested in retrieving all the subclasses because let's say if X is of type Y and Y is a subclass of Z, then automatically X is also of type Z, right? So for example, there is Honda. So Honda, it's a car. So Honda is a type of car. So Honda is a type of, say, motored vehicle. and motored vehicle is a subclass of vehicle. So if Honda is a type of motored vehicle, then it's automatically a type of vehicle, right? So that is the inference that you want to make here. So that's why you're interested in all the subclasses of this particular Y, right? But you can do that in a single line using the star operator. So this simply indicates that there can be 0 or more of subclasses. So X is of type Y, and now Y can have 0 or more subclasses, and you are interested in all such subclasses as well. And you can do the same thing for subproperties also. So subproperty, an example of subproperty is say has son is a subproperty of has child. So if X has son Y, then it automatically means that X has child Y, right? So you can also retrieve all such subproperties. Okay. So I don't know if so maybe I'll skip to some examples. Okay, let me.
It is 11:06.
Right. So I have another 25 minutes, right?
Yeah, true.
Okay, so
You can plan accordingly.
okay, so let me just describe this ask and then talk about this ask and then I can skip to the some examples. So ask, as I said earlier, it's similar to your exist, right? Although there is an exist in SPARQL as well, but in terms of how it acts, it's like exist. So it gives back a Boolean result saying whether this particular query pattern exists or not. It doesn't give out any particular result other than the Boolean value. So for example, you have your data here, triples. So there are two people, A and B, and you have a name homepage for A, name and mailbox for B. Now you are checking whether this particular pattern matches with the graph or not. So you are interested in X. X has a fourth name, and that name is Alice. So you are simply checking whether this pattern exists, and if there is a binding, it gives back the answer as true, and if there is no binding, then it drops that, right? So there is a false here. So it just returns true or false. So this is useful to check whether, let's say, you are interested in a few bindings, and maybe you don't want to construct the entire query just based on the so if you write a big query, right, and then if you send it to the server, and if it's processing over a very large RDF graph, then you are blocking the server. You are taking up some computational resource of the server. So instead of that, let's say if you check some key query patterns. So let's say there are 10, it's a join on 10. You are not retrieving all that 100,000 results back to the client. You are simply saying that there is a binding. So if you get this result, then based on that, maybe you can be sure that there is something that can be bound to these subqueries, and you can use that information to build larger queries. So that's one use case for ask. So this is the other example where it says there is no binding for it. So here you are interested in X that has a name called Alice, and this is a shortcut. Right? So whenever you use semicolon, that means that you can, even for second BGP, the same subject can be repeated. So even for second BGP, it's the same X. So X has a mailbox, which is Alice. So if you are interested in only those bindings that satisfy these two criteria. So if you go back here, so you're interested in mailbox and name, right? So so in the case of A, you have Alice has a home page, but not mailbox. But Bob has a mailbox. So here you are saying that Alice should have a mailbox, which is not the case. So it returns false. Right. So let me take a break here, and then I'll. So first, if you have any questions, do let me know. If not, I'll switch over to the SPARQL queries. So running them, I'll run a few queries over some SPARQL endpoints, and then we can just check the results. And I'll go over these queries as well.
So we have 5 minutes again to chit chat.
Right. Yeah.
Yeah. So dear participants, all yours. You could ask regarding the semantic intelligence, whatever you feel like. Our expert is there, and even SPARQL. Any other open source tools other than SPARQL queries? Other than SPARQL queries.
Okay. So I think maybe Dr. Maya Ramnath, right? So maybe she would have briefly discussed it. So there are. So again, at the end of the day, this is a graph. And the very first day, I think I explained the difference between a regular graph and a knowledge graph, right? But if you just look at it, it's a graph. So you can use any graph query language, and SPARQL happens to be one of the graph query languages, as I said earlier. So there are few other popular graph query languages, but SPARQL is standardized, right? So it's a W3C standard. So that has its own advantages, but you can also use other query languages like Gremlin, for example. I can type it in. So there is Gremlin, then there is Cypher, there is GraphQL. So all these are graph query languages, and but the disadvantage is they are not standardized. So there's a chance that each triple store can implement its own query language, and you cannot use the same query language on a different triple store. Let's say after I don't know 2 years, you realize that the triple store is not very efficient, and now you want to change your triple store. So you have to rewrite all your queries into a different query language. But on the other hand, if you use triple stores like say Virtue, so that supports SPARQL. So no matter, even if you change your triple store, you can still stick to the same queries. You don't have to rewrite all your queries, right? So that's one advantage of standardization. Okay, so yeah, so you can use these query languages.
What is the difference between IRI, URI, and URL?
Okay, so yeah, so I didn't cover that. I don't know if yeah anyone discussed about this RTF graphs, right? So anyway, so each resource in either RTF graph or an ontology. So in ontology, you have these concepts and properties, right? And in RTF graph, you have these subject, predicate, and object. So all these are in general considered as resources. So all these resources should have a unique identifier, and that identifier is what is called as an IRI. So IRI stands for Internationalized Resource Identifier. So let me start with URL, and then we can go to URI and IRI. Right? So URL, as you all know, it's okay. So the point that is common to all of them is that all of them are used to point to a particular resource uniquely. So it's a unique identifier for a particular resource. So that resource can be a document on the web, or it can be a person, or it can be a chair, for example. It can be a living thing or non-living thing. Right? So it doesn't matter. But all these three are used to uniquely identify any resource. So in the case of URL, it happens to be a web document, and the other characteristic of a URL it's browsable. So you can put it in a web browser, and it will retrieve the URL. So it will retrieve the resource identified by the URL, and it will display it on the browser. Right. So those are the characteristics of a URL. So URI, it's similar to URL in the sense that it's also used to uniquely identify a particular resource, but that resource need not be a web document. It can be a web document, or it need not be. So it can be a chair, for example, chair in a room, or it can be a person, or it can be an aeroplane, right? It can be anything. So the other difference between URL and URI is that URI need not be browsable. So you don't have to necessarily get a web document back if you put the URI in the web browser, right? But it is generally considered a good practice to have some information associated with the resource. So for example, you are describing a chair. You have a URI to identify a chair. So it's always a good idea to have some information for both the man and the machine. Right? By man I mean human, right? Both for humans and machine. So URLs are primarily for human consumption, right? So you put in a URL in the browser and you get a document back, and that document can be read by the humans. So in the case of URI also, it's a good practice to associate some human readable information so that when you put that URI in the browser, something shows up. But it's not a requirement. So that's the difference. So the difference between URI and IRI is the encoding scheme. Right? So in URI, you have the ASCII encoding scheme. So that means it doesn't support the special characters. So let's say you have a special character like, it's called umlaut, right? So you have the U with the caret on top, caret symbol on top. So that's a special character. And there are a couple of other special characters. So you have the E with the tilde symbol. So it's not a tilde, it's a slash symbol, right? Something like E followed by this one. So, but this the symbol is right on top of the E, right? So these are special characters, and URI ASCII encoding scheme does not support these special characters. But on the other hand, IRI has this UTF-8 encoding scheme, which is much broader than ASCII encoding scheme. So it supports all these special characters, right? But all the other things of URI, all the other characteristics are same for IRI also. But in semantic web, we generally use IRIs. So we use IRIs to uniquely identify any resource. So be it a concept, property, or anything in the knowledge graph. So that's the long-winded answer for all these three. Sorry. Okay.
If you want, you could finish up your session even, and
Right.
we can put the queries in the FAQ also.
Right. So yeah, we can do that. So I'll just show you at least a couple of queries. Okay, so first thing is the SPARQL endpoint. Right. So DBpedia is a popular knowledge graph or a resource, especially in the semantic web community. So DBpedia is the structured version of Wikipedia. So I think all of you would be familiar with Wikipedia, right? And in Wikipedia, you have your info box. So let's look at one example of Wikipedia page, say Narendra Modi's Wikipedia page. So you have lots of information, right, about this person. And on the most wiki pages would have on the right hand side what is called as the info box. So this info box generally is in the form of keys and values, right? So you have a key and a value associated with it. Sometimes it's multiple values, but you do have a key and a value. So DBpedia is mostly extracted from these info boxes. So they take this info box and they convert that to triple. So in this case, the subject is Narendra Modi. So you can form triples, right? Narendra Modi, president. Okay, so this is not a good example. So here it refers to the president when Narendra Modi was in the term as prime minister, right? So in this case, you do need to make some modifications, but okay, that example works for, let's say, born, right? So Narendra Modi born as Narendra Damodar Das Modi, right? And Narendra Modi was born on this particular date. So he was born at this particular location, right? So yeah, you can use, or you can easily convert this info box into triples. So that's the whole point. So DBpedia is constructed from Wikipedia using these info boxes. And it's a very large knowledge graph or RDF graph, whatever terminology you want to use. and you can query it. So this is one of the SPARQL endpoints. So I mentioned about this SPARQL endpoint right at the beginning, right? So these are like web services that you can use to send in your query, and it will just retrieve the result. So you can go here, you can put in any SPARQL query that is of your interest, and you can run the query. So it will give out the result, right? So the advantage is that you don't have to write any program, or you don't have to have host a server to test your SPARQL queries. Or if you want to practice your SPARQL querying, this is a good resource. You simply type in and then check the result. So I'll show you a couple of examples. So again, this is from DBpedia, and right, so there's the wiki DBpedia page, and right towards the end, you have a couple of examples of queries, right? So you can click on these examples. So I clicked on the first one. So I'll close this. So you, and it will, these other endpoint, right? This is also the one of the endpoints for DBpedia. So it has listed out the query and the results as well in a nice tabular form. So the query that is of interest to us is people who were born in Berlin. So we are specifying the city, and we are also specifying the year. So they should be born before 1900, right? So let's take a look at this query. So you are interested in the people who are born before a certain year. So I think from the query point of view, just the name would have sufficed, but you are getting all these other variables as well. So now let's look at these queries. So DBO stands for DBpedia ontology. It's just a short, it's a prefix, right? So you can look up these prefixes here. So there's a relation that's already defined as part of the ontology, which is birthplace. So the person has to be born in Berlin, and now you are retrieving the birth date of this person, right? Because you have to compare with 1900, right? So the person has a birth date, which is represented by this variable birth, and you are also interested in the name of this person. And okay, I don't know why this death date is important, because that's not part of the query, right? So we can also ignore this. But the other important thing is the filter clause. So you are interested in only those people who are born before 1900, right? So before 1st Jan 1900. So that's what this says. And you are simply ordering by name. So this is also in SQL. Right? It will sort the names in ascending order by default. So that's what happens. So you are interested in the name, the birth date, and all. Okay, this is the third column is not important, and then you have the name of the person. Sorry, the IRA of the person, right? So that's what this is. So that then you get all these people who are born in Berlin before 1900, right? So it's a long list of people. So let us look at, I know this is much simpler, right? It's musicians who were born in Berlin. Okay, so first thing is they should be, this person should be a musician. I mean, this person can have multiple different employment types, right? So, but one of them, the one that we are interested in is that they should be musicians. And the second criteria is that they should be born in Berlin, right?
So it's not visible, sir. Is there any possibility to zoom or okay?
Oh, it's very small, is it?
Yeah, yes, sir.
Okay. So okay, let me put this query in
On a text box.
in a text file.
Yeah, sure.
Is this better?
Yes, sir. Yes. Fine, sir. Thank you.
Okay. So you are interested in those people who are musicians and who are born in Berlin. So basically Berlin musicians, right? So again, so you're okay, we can ignore this. So you have your name. Name of the person is important, but this person should be a musical artist. So A is a shortcut for RDF type. So this is just a shortcut, right? So RDF type indicates the type of this particular resource. So in this case, in the example that I generally give, Raghava works at AAA Delhi. The type of Raghava is faculty and the type of triple is university. So here you are interested in all those people who are of type musical artist, right? And DBO indicates that is from the ontology, DBPD ontology. So there is a concept called musical artist in the ontology, and you are interested in all the instances of this particular type, right? And the second BGP is that this person should obviously be born in Berlin, because that was the part of the query, right? So we are interested in the musicians who are born in Berlin. So the birthplace should be Berlin. That is fixed. And along with that, we are also retrieving a few other details of this particular person. So what is the birth date and the name of this person, and any other comment that is associated with this person. Right? So the other criteria that we are putting in is that the description of this particular person should be in English. The language should be English. And you are again sorting the name by ascending order. Right? So that is the query, and then you get all these as the results. So we can take one of these musicians, right? So you have Achim. There's a birth date associated with this person. There's a description which is in English, because that's what you wanted. And then there's the IRI associated with this person. So you can go to this IRI and then browse further. Okay, so it's not a browse. So it's not browsable, but it retrieves details of this particular person that you selected. Right? Okay, so that's the example of musician. So we have slightly more complex example here. Okay, and this is a simpler example. Maybe we start with this. So we are interested in retrieving all the games. So any game that has been played, or if it is categorized as a game, and we want to take a look at that, right? So okay, so we want the title of the game, and this game should be, again, A is used, so A means RTF type. So this game should be of type concept game, right? So this has been defined in the DPD ontology. So there is a concept called game, and you are now looking for all the instances of this particular concept. And along with the first criteria, there is a second criteria where you are retrieving the name of that particular game. Right? So that's the simple query. And all these are different games, right? Although several of them don't make sense, but this is part of the graph. Right? This information is part of the graph. Like, okay, I see chess there, so yeah, there are chess and different other games, right? Okay, then we'll look at this. This is more complex. So, so we are interested in soccer players who are born in any country. So that can be, we are not specifying the country, but that we are giving the description of that country. So this country should have more than 10 million people, and there should be a goalkeeper associated with this set of soccer team, or one of the soccer players should be a goalkeeper. And now we are giving the information about the club that the goalkeeper is associated with. So this club should have a stadium with more than 30,000 seats, right? And then the club country is different from the birth country. So this happens very frequently, right? So let's say there are people who are born in Germany, but they play for a club that is not in Germany, right? It could be a club that is in UK or any other country, right? So the birth country of the player is different from the club country. And the place that the person was born in should have more than 10 million people. So these are the criteria that you put for the soccer player, right? And then in order to write this query, it's okay, it will need a few. So this is a query that has lot of, okay, where is this? Oh God. So this is a query that has lot of joins, right? So you have semicolon here after every BGP. So that means, so until here, the subject is the same, which is soccer player. So you are joining on the subject, which is soccer player, and in the other set of BGPs, you are joining here. Okay, there's no joins here. So for this BGP, you are joining on the team, and for this BGP, two BGPs, you are joining on the country of birth, and the last one there's only one triple patterns, and so there's no join here, right? So if we count the number of BGPs, right, there are quite a few. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So this is an example of a slightly complex query, right, which involves lots of basic graph patterns. And this is also one of the differences between SQL and SPARQL, right? Generally, in SPARQL, you end up writing lots of joins, which may not be the case generally with SQL. So the processing time is also longer because it involves lots of joins. And especially on graphs that are very big, like DBpedia, you end up, SPARQL queries can end up taking a lot of time. So that's why you see this limit clause getting used. So in some of the queries, you might have seen the limit 100, right? So what this does is, it will limit the results. So let's say there are 100,000 results. So it will only retrieve the 100 results among them, the first 100, for example. So that places, that reduces the load on the server as well as the client. So now the client doesn't have to look at 100,000 results. So that's the last example. So with that, I'll stop. So if you have any queries, quick queries, I can take them. I don't know. So I don't know when the next session is about to start. Oh, you are on mute.
Will not be taking many queries. If there is some query who could ask by speaking, we'll take only one because we'll have the next session at 11:45.
Okay, sure.
Is there some participant who want to ask something very urgent? No. Yeah, I can see regarding UNL, there are queries from Mr. Dinesh every time. So yes, we will put it in fact, and we'll try to answer regarding this universal networking language. I'm very new to this, so I also cannot answer it immediately. So
yeah, I'm not aware of this universal networking.
I've also not heard of UNL, so we will look into it and we'll try our best to answer all the facts. I can see there are a lot of questions inside the fact list. It is 60 till now, 6060. I have shared the link also here. So our experts will try their best to answer those queries in fact.
So these queries were added by the participants, is it?
Yeah, in the chat boxes, we picked them from the chat box.
Okay.
And I feel that two of my scholars are the coordinators, Abhishek and Sumit. They might have added few from themselves also.
Okay.
So yes, we will prepare this fact for the FDP, so so that all can be benefited. So thanks, Raghava. Thank you so much for being here with us. And today is the Wednesday at 3 o'clock. If you get some time slot free, please be there. I have emailed the minute-to-minute schedule already.
Okay, so yeah, I may have to skip that. There are a few meetings that I need to attend.
I can understand. That is
yeah, but
that
yeah, thank you. Thank you all for this opportunity to present or talk about SPARQL and semantic web in general. Hopefully, all of you would have been inspired or would be interested in taking up using semantic web technologies in one of your projects, right?
Yeah, it is perfectly fine. Actually, I propose to conduct such workshops at least once in a year. I will try my best, and I hope all my experts will support me in that.
Right, I think yeah, it's a good idea to have these summer, winter schools and FDPs, so that more people can get to know about these technologies, and then they start using it in their work. Right? So
we will talk for it sometime later, but I definitely propose to have some summer school yearly for India.
Right. Yeah, I think that's a good idea.
So okay.
Yeah, thank you all. Thank you, Dr. Sarika.
Thank you. Bye-bye.
Yeah, bye.